Welcome back to my favorite universe. For this lecture, I want to highlight what is, in my judgment, one of the most important discoveries of the 20th century. And it relates to something that people have been thinking about across time and across culture. Because what has happened is, if you read through the text, religious text, even scientific, it won't matter. Look through the history of time at a culture's writings. And in there you will find that people have looked up at their night sky and wondered, what is their place in the cosmos? Where did it all begin? Where is it all going to end? These are common themes. So maybe those questions are genetically encoded within us. And this particular lecture, titled Forged in the Stars, is a discussion of what is the origin of the elements that make up the human body, that make up Earth itself, that make up everything that is not just hydrogen and helium in the cosmos. Most people don't know the origin of the elements. Now, how's that possible when I just told you that it's, in my judgment, the most important discovery in any field in the 20th century? Most likely you don't know about it because it was not your classical kind of discovery where you have the lone genius burning the midnight oil, saying Eureka in the wee hours of the morning, and then being rushed by the press to find out what the discovery was, and then you put headlines the next day. That's not how this discovery happened. So it's not a very media-friendly story, in spite of its importance. This particular discovery took many decades, many people. It uses complicated math, and it's very hard to create sound bites out of it. So this was the nature of the discovery of the origin of the elements. And that is the subject of this lecture. I can tell you now the elements in the cosmos have two primary origins. One of them is the Big Bang itself. We got all of our hydrogen and most of our helium from the Big Bang. Everything else came from stars. The crucible in the center of stars. This hot place. In particular, one variety of star that has very high mass is a star that ultimately explodes. We call them supernovae, mentioned several times in previous lectures. Supernovae, if you study how they manufacture elements and how they explode and distribute them in the galaxy, you learn not only that such elements exist, you get the relative mix of the elements that we find in the universe, and you find out where they're distributed in the galaxy. You get all that for free once you understand how supernovae work. We trace that knowledge to a seminal research paper. It came out in 1957. It was published in the Reviews of Modern Physics, a respected journal. It was titled, The Synthesis of the Elements in Stars. How much more simple can you get? The authors were Margaret Burbidge, Jeff Burbidge, they were a husband and wife team, along with William Fowler and the inimitable Fred Hoyle himself. Fred Hoyle's a brilliant man, known for his extraordinary ideas that are occasionally correct, and as a participant in this paper, this was one of them. One of his crazy, brilliant, correct ideas. The 40 years prior to 1957, people had mused about whether the source of energy in the stars could be responsible for the transmutation of elements. People had wondered, but they had fragments of knowledge with which to make their picture. So there's a limit to how far they could go. But once enough time had passed and enough experimental data had accumulated, Burbidge, Fowler, and Hoyle brought together all of those pieces and implicated supernovae as the primary source of the existence of heaven elements in the galaxy. And this is what made that paper significant, but it was many decades in the making. So we have to ask the question. They're messy questions that led up to that. Messy. Like, how do the various elements on the periodic table of elements behave when subjected to extreme pressures and temperatures? You can't go visit the center of the sun, and ask and bring out your measuring devices. You'd be vaporized long before you got anywhere near it. You have to be cleverer than that. You have to trust the knowledge of your laws of physics. And you can do some experimenting, but that's about it. Do the elements, once you try to make them, do you fuse them together, or do big elements only break apart? Do you fuse them or fission? What's the predominant process? How easily is this accomplished? These are questions that were driving the results of that paper. When you have a reaction, does it give you energy? Is it exothermic? Or does it take energy away? Endothermic. That's a really important question with regard to the survival of a star, because stars are in the business of making energy. Not only that, the periodic table of elements itself. Can you explain that? It's more than just a chart of boxes sitting in the front of your chemistry class. There's a lot of action going on there. Can you start with hydrogen and helium, the birth ingredients of the universe, and manufacture all the other elements on that periodic table? Is that possible? Is that sufficient to synthesize everything on the table? If you could do that, that'd be kind of like modern alchemy. That's what everyone wanted to do. You read about the Merlin characters trying to, in their lab with test tubes, trying to turn base metals into gold. We can do that today. We know how to do that. The reason why they couldn't do it because they were experimenting in the domain of electromagnetism. They didn't know that they had to reach the domain of another force in order to transmutate the elements. They had to get into the nucleus of the atom. And electromagnetism doesn't go there. The strong nuclear force does. Had they known about the strong nuclear force 500 years ago, they might have known how to get into the atom and split it and make two other kinds of atoms. But that's sort of the basic questions and a basic attempt to understand the formation of the elements. But there's another problem, a very real problem that it's hard or even impossible to deduce from first principles. And that is, what are the collision cross-sections of the nuclear pathways? That's fancy talk, but it's not anything deeper than if you have two particles and I want to slam them together, how big a target are they to each other? Are they small so that your aim has to be really good? Or do they somehow take up more space so that when you slam them together, they're very likely to hit each other? So that we call that a collision cross-section. You have an intuitive sense of this because when you're, on a highway and they have like the wide load, the double wide load coming, double wide house, that has a large cross-section. So they have to take tremendous precautions so that nothing collides with it. In atomic physics, you want to know what that cross-section is. You want to know it exactly so that when you start bringing your ingredients together, you'll know who's going to hit who, at what rate, and who's going to do it the best or the slowest or the fastest. And it's from that you derive the nuclear pathways of what goes on in your soup of atoms. If you get the wrong cross-sections, you have no idea what's going on. You might as well just give up and go home. Because one wrong cross-section in your calculation will give you a picture that'll spawn all kinds of other reactions that would have never happened in the first place. It'd be like going into the New York City subway system, but with a map of the London subway, trying to navigate through the New York City system. That's just not going to work. So collision cross-sections are important to learn and important to know. So yes, this whole effort is difficult. And it, like I said, it did not lend itself to sound bites. Now, others, yes, had thought about the general problem. One of the most brilliant astrophysicists of the turn of the century, Sir Arthur Eddington, from a seminal book that he wrote titled The Internal Constitution of the Stars, he suspected, I quote from that book, "I think that the suspicion has been generally entertained that the stars are the crucibles in which the lighter atoms, which abound in the nebulae, are compounded into more complex elements." People knew the universe had had larger elements. They knew. You ask, well, where did it come from? Was the universe born that way? Well, this is way before the Big Bang. So they had either somehow the universe happened that way, or they're made. And he suspected that they were made. In 1920, atomic physics was going strong. There was the beginnings of nuclear physics, but it was the dawn of quantum mechanics. The full understanding of particles and atoms and nuclei was still to come. But he suspected that they were on the right track. You could ask the question, where else in the entire cosmos would you make heavy elements but for the centers of stars? You want an exotic environment. You want an environment that if you have to slam light elements together to make heavy elements, where's that going to happen? It's not going to happen in your backyard. It's not going to happen in your kitchen. You need something as hot as you can imagine. And that's the centers of stars. That was well known at the time. But the real solution required the discovery of quantum mechanics in the 1920s. There's no way Eddington could have figured out the whole story. He was missing physics. Physics had to be invented to complete that story. Quantum mechanics, as I've alluded to many times, is the science of very small things. Atoms and molecules. Something to consider. Protons, if you want a hydrogen nucleus is a single proton. It's the lightest element, the simplest element. If you want to bring two hydrogen nuclei together, they're both positively charged. They're going to repel. They're going to repel. And so what do you do about it? Well, slam them together faster. They'll get a little closer before they repel. How do you make it go faster? One way to do it is to heat the soup. Heated gases, the particles move faster and faster and faster as the temperature rises. Get them close enough together so that they're within the domain of the strong nuclear force. When you get them close enough together, the strong force kicks in and binds the two protons together. They had to cross this, what we call potential barrier, though, this electromagnetic resistance of the two positive charges. This electrical resistance, they had to overcome that. As I said in one earlier lecture, it's like taking a toy truck and sort of rolling it up a hill, but you don't give it enough energy and it just sort of rolls back, and you sort of roll it a little faster. It gets higher up the hill and rolls back. But there's a speed with which you can roll it, and it hits all the way at the top and goes over. That's what's going on with these protons. Now, Eddington is not stupid. Eddington calculated the temperature of the center of a star. He got that right. You don't need quantum mechanics for that. He said it's 10 million degrees or so. Then he calculated the speed with which protons must approach each other in order to collide. You know what temperature he got? He got 1 billion degrees. That worried him because the two temperatures had no correspondence with. They are vastly different temperatures. If you want to rely on collisions in order to give you a heavier element, you might be telling yourself at this point, the stars are not the place. As hot as they are, it's not going to work. Tens of millions of degrees is far away from 1 billion degrees. So that's why there was as much resistance as there was at that time for considering stars to be the place where heavy elements would be formed. But there were the diehards that said, look, I don't care what you say. I don't know what you're saying. All I know is the hottest place I can think of is the center of the star in the whole galaxy. So if you want interesting atomic things to happen, nuclear things to happen, if we don't look there, I don't know where else to look. And that's the right attitude. Because it turns out that the speed of protons at 10 million degrees is enough to make them collide. but not by the traditional way you might think. There's a phenomenon in quantum mechanics that has no analog in everyday life, and it's called tunneling. Tunneling. Let's go back to my little truck. I'm trying to roll it up the hill. Here I'm trying to shove it up the hill, and it rolls back, and it's not enough energy. In quantum mechanics, depending on the ambient temperature and pressure and conditions, one of these times I roll the truck, a hole opens up through the mountain, and it goes through the mountain and comes out the other side. And it gets to the other side of that mountain for free. Now, that'd be pretty interesting if that happened in everyday life. But it doesn't. It happens in the realm of the atom. So that, in fact, these protons, which are trying to overcome their repulsion, some of them actually do connect at temperatures as low as tens of millions of degrees. You didn't need the billion degrees, but before quantum mechanics was discovered, there was no way to think about that problem. There was no way to answer that problem. There was no solution waiting for you. All right. Quantum mechanics tells us, all right, the temperature's hot enough to make your elements. That's good. Well, how about the relative amount of each element? That's another kind of question to ask of the star. Well, come the 1920s are over. Quantum mechanics is in the can. 1931, there's an astrophysicist named Robert Atkinson. He published an extensive paper on what was going on inside of stars. And his abstract summarizes what he was after. Synthesis theory of stellar energy and of the origin of the elements, in which the various chemical elements are built up step by step from the lighter ones in stellar interiors by the successive incorporation of protons and electrons one at a time. So, we already accounted for the existence of elements, and he's trying to find a way where one by one you build up the elements. And in his paper, he talks about what kind of relative populations of the elements you would get. But he didn't have a chance of getting the right answer. He was missing a particle. He had the right physics, he's missing a particle. A year later, 1932, James Chadwick discovers the neutron. Now, you can't talk about nuclear physics without a neutron. Neutrons go hand in hand with protons in the nucleus. That's an incomplete theory. You left the salt out of the soup. No matter how smart you are, you weren't going to get the right answer without the neutron. Now, the fun part about neutrons is they don't have a charge. So here's a nucleus with this fat positive charge, and you take a neutron and toss it towards the nucleus, it just walks in the front door. There's nothing to resist it. So you can have a nucleus, feed it neutrons, and build up the count of particles inside the nucleus. You hand a neutron to the nucleus. No, it doesn't change the species. It's still hydrogen if you add a neutron to it. But we have a term for it. It's called an isotope. An isotope of an element is where you have a varying number of neutrons. You keep the number of protons for this. It turns out there are some elements where if you give them an extra neutron, they don't like the extra neutron. So spontaneously, again, we learned this from quantum mechanics, spontaneously, it's got the neutron in the nucleus, and it said, neutron, give me a proton and an electron. The charges cancel between a proton and an electron, as they are neutral in the neutron in the first place. So all the charges work out. So you give the atom a neutron, the neutron spontaneously becomes a proton and releases an electron. So almost for free, I got to have a proton join my nucleus. This process is a very effective way of building up elements. And it can happen swiftly. There's some, by the way, it may be that there's some elements, not maybe, it is true, that there's some elements where if you give them one neutron, they go unstable and they kick the whole neutron out again. But if they have 2 neutrons, they are stable. And they're given the time, they'll convert the neutrons to protons. So think about it. If you have a weak flux of neutrons into your atoms and into your nuclei, if you're an atom that's unstable with a neutron, you're not going to do anything with it. If you're stable with a neutron, fine. You'll mutate it into the next element up on the periodic table. But if you have a heavy stream of neutrons, maybe I just gave you one and you're unstable, but before you could release that neutron, another one comes in. Now you've got 2. Turns out the nuclear physics of it say that I'm stable with 2, even when I was not stable with 1. So with 2 neutrons, I'm stable. Now I can undergo a decay again and turn my neutron into a proton and an electron. So it's simple. One is called slow neutron capture. The other is called fast neutron capture. The only lesson there is that now there are more ways to make elements. It's not just simply slamming protons together the macho way. There are also less spectacular ways of building up the population of elements on the periodic table. And when you combine all of those features, each one of them gives you a different mix of different elements, and put them all together, you begin to recover the exotic distribution of elements in the cosmos. You begin to recover why it is, for example, that on average, elements with an even number of protons are more abundant than the adjacent element that has an odd number of protons. That's odd. Those elements, they needed 2 particles to come in. You're actually slamming a helium nucleus in. You get 2 protons right off the bat. And you grow by just accumulating helium nuclei. So you're hopping in pairs. So if you look at the abundance on the chart, it's high here, down, high, down, all the way on up. Fascinating. And it all comes out of this analysis. Now, what about those collision cross-sections? Like I said, you don't get those. Those are hard. Those are hard. Turns out, just the facts of global politics, we got our collision cross-sections to feed the research that went into the 1957 paper by Burbage, Fowler, and Hoyle. Most of those collision cross-sections for the atomic nucleus came about from the research that went into the Manhattan Project, the American program to build the first atomic bomb in the Second World War. When you're at war, a lot of money gets spent. A lot of effort gets invested. Not because you're curious about the science, but because a weapon is being made. Your defense is paramount importance. And a sidelight of that fact, it's simple. A sidelight of that fact is we got from that research, once it became declassified, collisional cross-sections of particles moving in and out of an atomic nucleus. And it enabled those calculations in the first place. Now, of course, now that we know how to make the elements in the centers of stars, in particular in the centers of the high mass stars that have enough temperature and enough pressure to keep that going right on up the periodic table of elements, let's begin by asserting something that's not a strange concept, that stars are in the business of making energy. And to be in the business of making energy, that's all they know how to do. If you look at the sun, the cross-section of the sun, what you see is down in the center, that's the hottest place. It's much, much cooler out to the surface. And it's in the core, that's where all the thermonuclear fusion is going on. The sun is making heavier elements. It's converting hydrogen into helium. But that's not the interesting elements. The interesting ones are the ones that we're made of. So the ones we're made of, who's going to make those? Those are the high mass stars. They start out making hydrogen into helium, fusing the two, fusing hydrogen, becoming helium. There's a loss of mass there. You do the arithmetic. You start out with more mass than you ended up. What happened to the mass? It all got converted according to E equals mc squared, and you get an enormous amount of energy from that lost mass. All right, so now you go hydrogen and helium. High enough mass stars convert helium to carbon. They take 3 helium atoms and get carbon out of it. Then, if you have high enough mass, it'll keep cranking this through. It runs out of one element and starts manufacturing the next. It goes from helium to carbon, carbon to oxygen, oxygen to neon, and this continues. And it's getting energy at every phase, except it's not as efficient. It blows through those heavier elements very quickly, compared with how much time it spent converting hydrogen to helium. So, as it moves up the periodic table, one of the elements it's going to end up with is iron. Time to fuse iron. Well, let's go for it. All right, let's collapse a little bit, get the temperature up. We begin to fuse iron at extremely high temperatures, much higher than what the sun is doing right now, or at the centers of a star while it's converting hydrogen to helium. So we start fusing iron. There's a problem. If you fuse iron, it absorbs energy. It doesn't release energy. Now that's a bad day for the star, because a star only knows the creation of energy. It's that creation of energy that supports it from collapse. Without a source of energy, it is hosed. The star has nothing to hold itself up. So it gets to iron, it fuses iron. Not only is it not good for it, because it's not giving up any energy, it's actually absorbing energy. And the whole star destabilizes. And it collapses. It collapses in a matter of hours. And the collapse of that star rebounds from the center in a titanic explosion that is as luminous as 1 billion stars. And we call those objects supernovae. They're visible across the galaxy, across the universe. You're looking at an image of a galaxy halfway across the cosmos, and there's a little smudge there, but there's a bright light sticking on one of the spiral arms of a spiral galaxy. That's a supernova that just went off. These things happen in real time when they happen. You can watch them get brighter and watch them get dimmer as the explosion runs its course. Well, this is such an active place that, in fact, there's a lot of free neutrons running around and protons. And so not only did you manufacture elements on way to iron, there's a lot of manufacturing going on after iron as well. Slow neutron capture, fast neutron capture, a little bit extra fusion on the side. It is a trove of enriched chemical elements. One such remnant of a supernova is the Crab Nebula. The Crab Nebula is the remnant of a star that exploded and was seen. It was seen by the, well, actually, we think everyone on Earth saw it, but it was only recorded by the Chinese. AD 1054, July 4th. In the records of the Chinese records, there's a new star in the sky. We now know that was a supernova. We now know it was that supernova, making this residue, this explosive remains, this 2,000-year-old remains, which we have poetically referred to as the Crab Nebula. Now you notice on it, there are these fibrous parts to it. Each one of those areas contains a strand of heavy elements, lifted out of the center of the star and brought into the galaxy for the rest of the galaxy to share, so that subsequent stars that are made can make something other than the central star, like planets and even people. In the next one, it's another supernova remnant, Cassiopeia A, we happen to call it. It's in the constellation Cassiopeia. Cass A, you notice, once again, you'll see how sort of explosively thrust forth these gas clouds are. And if you analyze the chemical composition of each of those strands, you'll find very high iron and oxygen and carbon and all the things, all the elements that we've come to know and love as living beings that thrive on the heavy elements of the cosmos. So you combine all this. And what Burbage, Fowler, and Hoyle did was they took the well-tested tenets of quantum mechanics, combined it together with the physics of explosions and the latest collisional cross-sections for the atomic nuclei. And they also looked at all the nuclear pathways that can result based on those input parameters. Combine that also with basic stellar evolution theory. And when you've done all of that, and you've done your homework, you account for not only the existence, but the distribution and the relative abundance of elements in the cosmos. And it was in 1957 where it was determined something about us that I will never forget, and I will tell as many people as I possibly can. And you might have expected it all along, but it remains true, not just figuratively, but literally, that we are all stardust.